Hi guys, so today's the day we're going to try to calculate some of these or apply some of these principles to calculate volume, temperature, and pressure. So we've only looked at Charles and Boyle's law so far, so those are the two we're going to focus on today. It's very, very simple, nothing like stoic. So before we start, just remember that P, V, and T stand for pressure, volume, and temperature. Pressure is the force involved. Volume is going to be the space. I'll be right there. Temperature is going to be energy. And then just remember that the units of measurement that they have to be in, pressure has to be measured in kilopascals. Volume has to be measured in liters. And temperature has to be measured in Kelvin. So there's going to be a little bit of conversion, but nothing crazy. Okay, sorry, I'm back. I'm sure you guys have interruptions at home too, all your siblings, parents. Okay, so remember that Boyle's law says that pressure and volume do the opposite of each other. So one goes up, the other goes down, and vice versa. One goes down, the other goes up. So the formula actually shows you that it does that. So remember that we're dealing with more than one. So it's kind of like a before and after, like the P1, V1 is like the pressure volume before, P2, V2 would be the pressure volume after. So you're going to be missing one of these variables, so you just have to solve for it. It's basic algebra. So, oh, and over here, there's a little note that volumes need to be in liters and pressures are going to be measured in kilopascals. So I put an example here, and I'm going to follow the link because the link is already worked out and solved for us. And I'll upload these videos as well. So if you don't want to hear my voice talk, you can just watch the videos. But it says a sample of gas occupies a volume of 250 milliliters. So we're using context clues so that we know that this is going to be a volume. It's going to be volume 1. And I'm trying to like circle all of the numbers it's giving me. This ends in kilopascals, so I know that it's a pressure. So I'm going to label this as pressure. And I'm going to label both those ones. So those are my first volume and my first pressure. What volume will it occupy at 800 kilopascals? So again, we see kilopascals. That's a dead giveaway that that's a pressure. So I'm going to label that pressure too. What volume? The what tells me that I don't know what that is, and that's what I'm looking for. That's what I'm asking for. So you're going to put a V2. And what I like to do, it's just keeps it more organized. I go off to the side, and even though I labeled it in the word problem, I just kind of like to make my little notes on the side. So my V1 was 250 milliliters, but we already know because we stated it in a couple slides ago that milliliters won't do. We have to change this to liters. It's a very easy fix. All we have to do is move the decimal point back 3 spaces, and we've now converted from milliliters to liters. So really no math, just use your decimal skills of moving it over 3 times, and that will be your conversion. So V2, I don't know what this is, so I'm just gonna leave it as a question mark. And then I have P1 and P2 that I need to identify. So P1 is gonna be the first pressure that I encountered. It's already in kilopascals, so you don't have to do anything new. You're just gonna leave it in kilopascals. That's the unit of measurement you need, so no little conversion like we did before. And then our P2, we already identified it in our equation, our word problem, and it was 800 kilopascals. I had trouble drawing that 8. So 800 kilopascals. So now that I have identified everything, I have 1, 2, 3, 4 variables, and that's how many variables there are in my problem. V2 is the one I'm looking for, so I'm just going to circle it so that I know that that's the one I'm solving for, because now I have to do some basic algebra. I'm going to start plugging things in. So my P1 was 740 pascals. I'm going to go ahead and leave the units out because I've already converted everything and made sure. So there's no need for me to do all that extra writing. If I've already done my conversions, I can just keep writing my numbers. My V1 is going to be 0.25 liters. So whenever you see variables like this next to each other in an equation and there's no symbol between them, that means that they're being multiplied. So I'm putting my parentheses to show that I'm going to be multiplying. So then it's going to be equal to P2. And my P2, I've already been given a number for that, so I'm just going to plug that in. So it's just a lot of plugging in numbers after you've identified it. And then my V2 is what I'm looking for. I don't have it, so I'm just going to go ahead and write down V2 because I don't know what that is. Now I can start figuring out what I need to do. My goal is to get this V2 alone. Remember, if there's no sign between them, you assume that it's being multiplied. And so the opposite of multiplication is division. So if I divide by 800 on both sides, that allows me to get rid of 800 on the right side and get that V2 alone. And now it's just a matter of simplifying. So I'm going to do 740 times 0.25 divided by 800. And this is basic algebra, so you can use a calculator, of course. It's just about manipulating the equation. So the answer is 0.23. And another thing I wanted to note is that your V2 should be very close to your V1. And that's going to be an indication that you did this correct. And we're going to go ahead and look at the pressure one. Pressure one was 740 and pressure two was 800. So if the pressure is 740 and then it went up over here, that means that our V2, if our P2 went up, that means our V2 should go down. So that's what happened here. Our V1 was 25 and our V2 was 0.23. So you should always see like those things happening also. So that'll be another indication that you did this correctly. So I'm gonna exit out of there. I am gonna go ahead and attach the link to all of these later, but our next word problem is gonna be, again, with Boyle's law. This one says a sample of carbon dioxide occupies a volume, again, use those context clues, volume of 350 liters at 125 kilopascals. So this is liters, I know that's a volume, kilopascals, that's a pressure. What pressure tells me I don't know what that is, so I have to solve for that at some point. Would the gas exert if the volume was decreased to 2 liters? So volume 2, it's in liters, which is what we wanted. So this makes our job a lot easier on this problem because we don't have to convert. So we can write down our V1, which was 3.50 liters. Our V2 was 2 liters. Our P1, and I'm just writing down these variables that you have up here. I just like to keep them together for me, you can write them down however you want. But 125 kilopascals. All of these are already in the units we want, so there's no need for conversions. We don't have to move anything around. So P2, I'm gonna write down, and we don't know what P2 is, so I'm gonna go ahead and leave it as a question mark. And now it's our turn to go ahead and plug things into the main equation. We're looking for P2, so I'm just gonna circle that so that I know that that one I'm just gonna bring down. So our P1 is gonna be 125 kilopascals. And again, I don't really write down the units in the problem because I already did all my conversions to begin with, so it's just gonna waste time and effort if I just continue writing the same things down. So remember, when two variables are next to each other, you wanna make sure that you have parentheses or something to indicate that they're being multiplied. So our V1 was 3.5, and that's why we plug that in there. We don't know our P2, it's circled from the beginning, so we're gonna just drag that down. And then our V2, we're gonna square it over here so we can know what we're plugging in, and that's our 2. So again, these two are being multiplied by each other. Opposite of multiplication is going to be division because we're trying to get this P2 on its own. So we're gonna go ahead and divide by 2 because that's what we want to get rid of. But if we do it to one side, we have to do it to the other, just like algebra. So you cancel out the 2's on this side, and then you can simplify. You're going to do 125 times 3.5 divided by 2. So basic algebra, plugging stuff in, manipulating to get isolate. I think that's what you guys call it in math, isolate your variable, your unknown. So this is 218.75 kilopascals. And I know that because that was the unit I was using over here for pressure. And another thing I want to note really quickly is if you're unsure, just look at your original pressure. It should be in the same range. These are really big numbers and they seem far away. So another way that you can check yourself is volume 1 was 3.5 and volume 2 was 2. So volume went down. So that means pressure should go up. So the original pressure was 125 and P2 was 218. So that's the way you can check yourself if the trends are matching. One goes up, the other goes down, or vice versa. Okay, I'm gonna exit out of. And Charles' law does not have to do with pressure and volume. It has to do with volume and temperature. And the equation is going to not be multiplication, but division. V1 over T1 equals V2 over T2. It's a direct relationship. You can tell by the graph that they're increasing in the same direction and decreasing in the same direction. So they do the same thing. Charles' law of variables are going to be V1, T1, V2, and T2. So initial volume, initial temperature, final volume, final temperature. Volume is going to be measured in liters. Temperature should be measured in Kelvin. So that's the reason we did temperature conversions on Tuesday, because you need to change everything that you're given into Kelvin. The good thing is you pretty much are going to be only using this equation because we usually measure in Celsius. So all you have to do is add 273. It's technically 273.15, but a lot of people just round to 273, especially if you're solving, because the 0.15 will cancel out either way. Sorry about that. All right, so with this example, it's asking for a sample of nitrogen occupying a volume at 250 milliliters. So I'm already in my head making mental notes that 250 milliliters is going to have to be converted into liters. So I'm just putting those three little decimal place moving for my notes later. And then 25 degrees Celsius, this is a temperature, but I'm going to draw an arrow going to the formula because I know that I don't want degrees Celsius, I want Kelvin. What volume? So context clues, what volume is asking a question, so I don't know what that is. Will it occupy at 95 degrees Celsius? So this is another temperature, and temperatures need to be in Kelvin, so we're going to go ahead and do all these conversions when we get down to our notes that we take for plugging in. So V1 is going to be 250 milliliters. We don't want milliliters, so we got to move the decimal back 3 times in order to make it liters. That'll be 0.25 liters. Our V2, we don't know. We have a question mark there, so sorry about that. We have a question mark there, so that's something that we're going to need to solve for. And then our T1 is going to be 25 degrees Celsius. I already made a note for myself up here saying that I don't want degrees Celsius. I need to add 273.15. Like I said before, a lot of people just round to 273. The formula technically says 273.15, but if you think about it, those will cancel each other out anyways, so it's almost negligible. So when you add 273, you get 298, and then our T2 we have to do the same thing with because it also came to us in 95 degrees Celsius. So 95 degrees Celsius plus 273, and that'll give you your temperature in Kelvin. The good thing is that usually you measure in in Celsius, so you're pretty much always going to use this one formula, just adding 273. So that ends up being, I think, 368 Kelvin. And now we're ready to plug things in. And this is division. So what we're going to do is I'm going to color code this a little bit differently so it makes more sense. So our V1, we have to put on top. Our V1 is going to be 0.25. And that's going to be over temperature. So over T1. So our T1, we already converted and everything. So this is just plugging in. It's all simple after this. So our T1 is going to be 298. And we're done with the left side of the equation and can move on to the right side of the equation. So this is going to be V2, which we don't have. So I'm just going to bring that V2 down. I know we don't have it because I wrote it in my notes over here. The question's asking for it. Lots of indications that I don't know what it is. And then the T2, we already identified over here. So that's going to be 368. So we're going to plug that in at the bottom. Okay, so basic algebra, if you are trying to isolate a variable, in this case, the variable is V2, you need to get rid of whatever's on that side with V2. So this bar right here means there's being divided. So the opposite of division is multiplication. And we're gonna multiply by whatever we're trying to get rid of. So we wanna get rid of this 368. But if we do that to this side, we gotta do it to the other side, keep things even. So what will happen is that the 368 will cancel out on the right side, but on the left, there's nothing to cancel out with, so you're gonna have to do a little bit of math. So the V2 stayed alone, which was our goal, that's great. So we have 368, and you need to multiply that by 0.25 divided by 298, which should be a very, very small number. 0.00083. And then we're almost done. You just need to multiply those two, 368 times 0.00083. And your answer is 0.3 liters, 31 liters. So notice our answer, 0.31 liters, is very close to our V2 is close to our V1, which was 0.25 liters. And Charles' law states that these actually are directly related. So let's look at our T's since we had both of our T's. T1 was 298 and it increased to 368. So we should see the same thing with volume. So our V1 was 0.25. It should increase, and it did, to 0.31. So we know we did that problem correctly. Okay. And one more example problem before I set you guys free. This is also Charles' law. And this one says that oxygen gas is at a temperature of 40 degrees Celsius. So we're gonna have to do a little converting because we don't want anything in degrees Celsius for temperature. That's our T1. When it occupies a volume of 2.3 liters, use your context clues. It tells you it's a volume, so you know it's a volume. So V1 also says liters, so you know it's a volume. What temperature? When it's asking what, we don't know what that is, so we have to look it up or solve for it. So T2 is unknown. Should it be raised to occupy a volume, so another volume, so that's going to be V2 since we already have a V1 of 6.5 liters. Off to the side, I would list your variables. So V1, V1, we'll start with the V's. V1 is 2.3 liters. It's already in liters, yay, we don't have to convert. V2 is going to be 6.5 liters. Part of the reason I do this also is so I can do my conversions off to the side and they're not like messy when I don't get confused when I'm plugging stuff in. Like plugging in should be the easiest thing. Our T1 is going to be 40 degrees Celsius, but we know we can't do Celsius when we do these problems, so we have to go ahead and add 273. So that ended up being 313. And then our T2 was going to be unknown. We don't know what the T2 is. So this one's a little bit weird because you're going to have the T2 on the bottom this time. So let me show you how to work this one out. So start plugging stuff in. Our V1 is 2.3 liters. And that's going to be over our T1. Just write my fractions out now. Our T1 is going to be 313, so that's going to be at the bottom. And then that's going to be equal to our V2. We actually have our V2 this time, so we have 6.5 on the top. And then our T2 is unknown. Okay, so I'm going to pause right here really quickly just so we can analyze a little bit. So these are direct relationships. We have our volumes at the top and our temperatures at the bottom. Volume 1 is smaller than, it's going to increase over volume 2. So volume 1 is smaller than volume 2. There was an increase. So that means if there was an increase in the volumes, we should see an increase in the temperature. So we should get a number at the end of this bigger than 313. Another thing to notice is 2.3 to 6, that's a multiple of 3, right? 2 times 3 is 6. So the 313 should also be increased since they're a direct relationship. It should increase by a factor of 3. So 313, we should get something in the 900s. And this is me just already predicting in my head. Also, I already worked out the problem, but it still makes sense. So the way that you would solve this is a little bit different. I would, in this case, because the T2 is at the bottom and that's a little bit trickier to work with, what I would do is I would go ahead and solve 2.3 divided by 313 first. That way you have one number on the left side to work with. So that should be something really small. And then once you have one number on the other side, it's really easy now because all you have to do is, we want to isolate this T2. All we have to do is switch over T2 with the 0.07. We basically have to swap their places, kind of like cross multiplying. And we'll get the T2 alone, and we'll have 6.5 on top divided by 0.007 because that was what switched places with the T2 in the first place. So it seems really difficult, like, to manipulate everything, but it's not if you just solve the left side first and then switch over whatever's in the bottom. And so then what we're left to do with is simplify. So our T2 should be equal to 6.5 divided by 0.007, which is 9 and it's always in Kelvin, temperature's always in Kelvin. So it was as predicted because 2 increased by about a factor of 3. The 313 should have increased by a factor of 3, which it kind of did. So that's another easy way you can check yourself. I'm gonna exit out of this. Your assignment will be linked into the Google Classroom, and it'll also appear as something that you have to do. I'm gonna upload these examples. I'm gonna put the links on the Google Classroom. However, they won't be narrated, but maybe some of you will prefer that. So if you need any help with today's assignment, please reach out to me. I'm willing to work problems out with you. I'm willing to answer all your questions. So reach out if you need anything. Thanks, guys.